All right, lecture 13, the last lecture before the midterm. We're gonna wrap up what we call geometrical optics, which is ray tracing of optical elements. So we're gonna talk about curved mirrors, and then the last topic is about interference of light. It's a little bit strange that I put it here. I should have put it a little bit earlier than this, but I kind of decide to do it this way. But those are the two topics that we're going to talk about. So let's review quickly what we talked about in lecture 12. In lecture 12, we talk about an optical element called lenses. Okay, so last time we talk about two things. First is what we call converging lens. Okay, a converging lens. This is called a convex lens or converging lens. Either term is fine, okay? But again, personally, I like the term converging lens more because that tells you right away what the lens is doing, okay? So converging lens, like the name suggests, is gonna converge light ray. So the main kind of property of this kind of lens is that if you have light coming from the left, okay, so light gonna come in a straight line, right? Parallel ray like this. And the role of this lens is to converge all the light ray into a single point. And that point depends on how you shape the lens, okay? So let's say I shape the lens such that the point is this one. So that means the light ray coming from the left will get converged onto this single point here, okay? Hence the name, converging lens. It's a bit hard to draw here. Okay, just draw by hand for the last one. Something like this, okay? The point where all the light ray meet, that particular point, that's called the focus of the lens or the focal point. And the distance from the focus of the lens to the lens is called the focal length. And that's the parameter that we use the letter F to stand for the focal length. Okay, so F equal to something. And for converging lens, we're gonna use F equal to positive number. So for example, it's gonna be plus 20 centimeters. So if you see plus in the focal length, then you know that the lens we are talking about is converging lens or convex lens. Okay, and we talked about the ray tracing diagram last time. We're not going to repeat that now because we're going to talk about it again anyway when we talk about curved mirrors. So if you don't remember, go back and look at lecture 12. The other kind of lens that we talk about is called diverging lens. Okay, as the name suggests, it's going to diverge the light ray hitting the lens. So it's going to look like this. Okay, so the middle section of the lens is going to be the thinnest part of the thinness compared to like the whole body of the lens. All right, so this is called concave lens or diverging lens. And again, we're gonna characterize the behavior by talking about what it's gonna do to all the light rays coming parallel. Some trouble drawing some, okay. Like this. Okay, so it's diverging, so it's not gonna go this way, it's gonna go out actually. And we can also define the focal length or the focus point, or the focal point or the focus of this kind of lens by doing it this way, right? So that's the focal point. But in this case, the focal point is when the light gonna get diverged. But then when you trace it back, they're all gonna meet at the same point over there. Okay, so something like this. So if you trace back, they're all gonna meet at the same point, right? They will not really meet, right, because the light is kind of like get diverged away, right? But the focal point is when you extend back all this light ray, and they're gonna meet at one point, and that's the focal length for this concave lens or diverging lens. So the focal length is defined to be the same, which is the distance from the lens to this particular point. And because of this, the focal length is going to be negative, for example, negative 15 centimeters for this kind of lens. Okay, so I mentioned already that for a simple lens means it's thin, so we need to, we can ignore the thickness of the lens. In reality, the lens is not thin, so what we calculate is not going to be 100% accurate, but that's good enough in most cases, right? So for a thin lens or a simple lens, the focal length alone is enough to say everything you want about the lens, right? So if you say that the focal length of the lens is plus 20 centimeters, then you know that it's a convex lens with the focal length of 20 centimeters. If you say that the focal length is minus 15, the minus sign tells you already that the lens we are talking about is diverging lens or concave lens, and the focal length is 15 centimeters. Okay, so this number, the F number alone is enough to say everything you want about the lens. So we have one equation which is called the lens equation, or the mirror equation if we use it for today material, which is for mirrors. So it's a mirror or lens equation. And it's a simple equation, 1 over F equal to 1 over SI plus 1 over SO, right? SI is the distance, the image distance. So it's defined to be the distance of the image to the lens. And SO is the object distance. So it's the distance from the object to the lens. Okay, and let me remind you like the sign convention that we have for the lens. For the mirror, it's gonna be kind of the same, but not really the same. You're gonna see it in a few moment. But for lens, okay, the sign convention is this. So SO, the object, is always positive. So we usually make it such that the object is on the left-hand side of the lens, but it actually doesn't have to be like that because, I mean, I don't know why that's the case, right? Maybe because I'm right-handed, but it doesn't matter where you put it, okay? But SO is always positive, right? It doesn't matter which way you put according to the lens. So what I mean is that if I have a lens and I have an object here, maybe a pencil or a tree, SO is just the distance from the object to the lens. Okay? Again, it doesn't matter if you put it on the left-hand side to the lens or the right-hand side to the lens. SO will be measured like this. Okay? So once you fix this, that's fine. You can use this equation to solve for SI, the image. Okay, and depending on the value of SO and also the type of the lens, which is the value of F, the focal length, you can have either positive or negative SI from solving this equation. So we're going to have two cases. Si, well, I should use different color. So Si is positive. This means pretty much two things. First, it means that image is on the other side of the lens. Okay, so I'm not sure whether I was this clear in the last lecture. Maybe I say it's on the right hand side, but I think the better way to say is it's the other side of the lens. It's the other side compared to the object, right? So if you have the object here, then the image gonna be somewhere here. Okay, that's what it means by positive Si. And the image is real and upside down. Okay, so it's gonna be something that looks like this. Real image means the light ray really intersect at that point. Okay, something like that. That also means if you put a piece of paper here, then you're gonna see an image projected on this paper. Okay, that's what we mean by real image. So think about a projector that you see in your classroom, right? The thing that your instructor used to project the screen of the computer onto the monitor onto the screen, so we can see the picture on the large white screen. Okay, that's what I mean by this, right? You can put something there, and you're gonna see the image on that piece of paper or the screen, because the light ray really converge and intersect on the paper, so the image is real. And when the image is real, it's gonna always be upside down. Okay, it's gonna be upside down. So you can think about like the projector in the classroom again. The image that you see on the large screen, it's not upside down, right? Because otherwise it's gonna be really hard to teach and to learn that way. So the image inside the projector, not the image, the object, which is the the screen, it's actually upside down, so that when you see it on the screen, it's going upright, so that you can see it and read it normally. So that's for positive Si. So what about negative Si? I'm not sure if I have enough space, so I write it somewhere here. Si is negative. Negative is just everything in the opposite direction. So image on the same side of the object. So it's going to be somewhere here. That's what I mean, on the same side of the object. Okay, and image is virtual. That means if you put some paper at where the image should be, you're not going to see anything, because there's no actual physical light ray meeting, converging, intersecting each other at that point, right? But you can see the image, because when the eyes see the light ray entering, the iris and retina, then the brain is kind of like fooled by the direction of the light ray. So the brain thinks that the image is there. Okay, but in reality it's not. So that's why we call it virtual. So the image is virtual, and virtual image is always going to be upright. So not upside down. Okay, so this is what we cover in lecture 12. So it's a quick review. Today we're going to talk about two more things, which is curved mirrors. One thing I'm going to say right away is that the physics of curved mirrors is going to be almost exactly the same as the physics of lenses that we talked about in the last lecture. So I'm going to write it here. the physics of convex lens or converging lens is going to be the same as concave mirror. What is concave mirror? Concave mirror is the mirror where the shiny part is on this side. So when I draw the mirror, I'm gonna draw the one with shading here. That's the back of the mirror. This is the front. The front is the shiny part, is the part that reflects light. Okay. So this is a concave mirror. Concave mirror gonna behave like convex lens. On the other hand, concave lens gonna behave like convex mirror. So it's kind of opposite, but you're gonna see what I mean in a few moments. So it's gonna be the other way around like this. Okay. But I mean, if you don't know what I'm talking about here, it's fine because we're gonna talk about it. But I just want to point out the important point right away is that what you're gonna learn for curved mirrors is nothing new. Okay, maybe 5% new, but I mean almost the same as what we learned about last time. And you're gonna see the similarity right away. Okay, so let's start talking about that. So I'm gonna start talking about this convex mirror because that's probably what you see more often compared to concave mirror. This is a convex mirror and you see this often in a parking lot, right? Because this is designed to help you see around the corner so that car accident can be avoided. So this is the first thing we're going to talk about. I'm going to explain this in more details later, but this is the diagram that I took from a textbook. It's a convex mirror. So that means the shiny part is this part here. So when I draw it, sometimes I'm going to draw it this way. I'm going to draw it like this. And then I'm going to shade the back like this. Right. So this is the back of the mirror. This is the front, the shiny part, right? So light ray gonna come from the left. So similar to the diagram I had on the left hand side. And then it's gonna bounce out like this. That's what's happening. Okay, and you see, remember what I talked about in the previous page. Concave lens behave like convex mirror. This is convex mirror. Why that's the case? Remember, convex mirror, not convex mirror, concave lens, which is the diverging lens. Its role is to diverge light away from the optical axis. And this is doing the same thing, right? You can see that the mirror itself is bounce light away from the optical axis, which is the center line like this. Right. So that's why the behavior of convex mirror, what we have here, is the same as diverging lens. Okay? So that's the reason. Because the role that is having is the same, right? It's going to do the same thing to the light ray. Okay. Before I start talking about the ray tracing for convex mirror, let me mention one important thing is that sometimes you're gonna hear the word spherical mirror. Now, spherical mirror is just a special category of curved mirror. So what we are talking about here, whether convex or concave mirror, are called curved mirror for obvious reason because it's not flat, right? For flat mirror is the mirror surface is flat, but this is not flat, it's curved, so we call it curved mirror. But the shape of the mirror which is curved, it actually can be anything, right? You can be as fancy as you want. Like in, you know, the when they construct telescopes, sometimes they use curved mirror, and they can shape the mirror into a three-dimensional parabola, which is called a paraboloid. Okay, that's also possible, but that require special equipment and a lot of money and time to make. An easier way to make curved mirror, which is not ideal but is good enough in most cases, is to start with a sphere. A sphere is a lot easier to do, to make in principle. And what you do is you want just one section of this sphere. So it's kind of like you cutting away what you don't want, and then you are left with just the section of a sphere. So on this screen, which is a two-dimensional projection of the sphere, you're gonna see as an arc of a circle, right? So it's a part of a circle, but remember, like actually it's a part of a sphere, right? So it's a three-dimensional thing. Okay, so this is what spherical mirror means, and most of the mirrors that you're gonna see in in this lecture, I think not most, like 100%, it's actually a spherical mirror. So I just want to make sure that when you see this term, you're not super confused. But anyway, because of the way you make the mirror, which is spherical, right? And you want it to be convex mirror. So what do? Well, after you cut it, right? You can, coat the back side of the mirror so that the other side is shiny. So you have a convex mirror, right? On the other hand, you can coat the opposite side. So that's the back of the mirror instead. So you have concave mirror, which we're going to talk about next, right? So that's fine. But because you make this from a sphere, any sphere will have one parameter which is called the radius of the sphere, right? So it can have different mirrors with different curvature, meaning that you can have different mirror with different, curvedness. And you can do that by starting from sphere of different size. So the radius of the sphere is r. Okay. So when you cut the sphere, the section left for you to make the mirror will also have the same radius of curvature, r, like this. Okay. And it can be shown, I'm not going to prove it to you, that something which is called a focal length of the mirror, okay, is actually just half of the radius of curvature. Okay, so if you start with a sphere of like radius equal to 20 centimeters, right? The focal length of your curved mirror after you cut out all the unwanted part, the focal length is going to be half of that. So 20 divided by 2 is going to be 10. Okay, but now whether it's positive 10 or negative 10, it depends on whether you talk about convex mirror or concave mirrors. Okay, but we're going to revisit this again soon. But this is something that you can remember, that if you know, well, so here's the thing. Sometimes in the problem, when you solve the problem, you need to know the focal length. And sometimes the focal length is not given to you directly when you talk about mirrors. So instead, the radius of curvature is given to you, right? So for example, there's going to be a problem says, consider a convex mirror where the radius of curvature is 40 centimeters, right? So you know right away that focal length is half of that, right? So it's just one more step to get the f value. And then you're going to use the f value to solve for anything you want using the lens equation. All right, we're going to talk about that soon. So let's talk about the ray tracing diagram. So I'm going to come back to this picture later before after we do it ourselves here. So let's be a little bit more specific. So example, all right. So example, let's consider a convex mirror with the radius of curvature equal to let's say 40 centimeters. An object is placed, let's say 50 centimeter, not 50, let's put it 30 centimeters from the mirror. Where is the image? Okay, so it's probably better if we just learn by example here. Okay, so a convex mirror with the radius of curvature 40 centimeters. The object is placed 30 centimeters from the mirror. Where is the image? Well, right away we can say that because radius of curvature is 40 centimeters, then the focal length is half of that. So it's going to be 20 centimeters. But because it's a convex mirror, the role of the convex mirror is the same as diverging lens. Remember, for diverging lens, the focal length is negative because it's diverge the light away from the optical axis. This is the same, so you need to put a minus sign here. So minus sign is because it's diverging light ray. Away from the optical axis. So we just put the minus sign like this, okay? So it's still radius over 2, r over 2, right? But you need to put in manually the minus sign because of the type of the mirror, right? Because next you can also have like concave mirror with the same radius of curvature. In that case, the focal length is going to be positive. All right, anyway, let's talk about the ray diagram. So the ray tracing diagram. Well, first, always you draw the optical axis, which is here. Okay, now comes the difference between mirrors and lenses. For lens, light can go through the other side of the lens because it's kind of like semi-transparent, like the lens is made from glass. But for mirrors, you only have reflection. Okay, so that's going to be something which is different. So no matter what happened, the physical light, the actual path is not going to enter the other side of the mirror because, you cannot do that. The back side of the mirror is inaccessible. So let's draw the mirror a little bit to the right. So let's draw it like this. So it's a convex mirror. Oh, sorry, it's actually the other way around. So like this. And this is the back side of the mirror. So I'm going to kind of do some, sometimes, people call it like an eyelash or something, right? So that's the curved mirror. And I would say f equal to minus 20 centimeters like this. Okay. So let's, what should we do in terms of the grid? Let's call one grid equal to 5 centimeters. All right. So what does the convex mirror do? So when the light comes in here, it's gonna bounce out like this, okay? But that's gonna be the same for every light pearl coming from the left. It's gonna bounce like this. But when you extend the light back, so I'm not drawing it very well here. So when you extend the light back, and by back here, it's actually on the other side of the mirror here, right? So this is the line that you kind of imagine that is there, right? You just put it, extend it from the actual physical path of the light, right? Again, the light cannot enter the back of the mirror, so it can only bounce also to the left. But you can extend the light back here, and they're gonna meet at one point, and that's the focal length of this convex mirror. So you can see that the concept is very similar to a diverging lens, right? So allow me to go back for 1 second and look at this, right? So it's almost the same thing except you flip this side of the picture onto the same side as the incoming ray. Everything else looks the same. Okay, so we are not really learning new things here. We're just learning another optical element which behaves exactly like a convex lens, like a concave lens, except it's made from mirrors. Okay, so everything will be very familiar to you, hopefully. So we can do the ray tracing without too much difficulty, hopefully. So let's first indicate where the focal point should be. The focal point is 20 centimeters, so each grid is 5, so it should be 4 grids. So 1, 2, 3, 4, it should be here. And then the object is 30 centimeters away from the mirror. So the object is 1, 2, 3, 4, 5, 6 over there. So the object is here, right? 30 centimeters away from the mirror. And then we're gonna draw 2 lines again. Now I might switch the color compared to what we did in lecture 12. But the first thing we're gonna do is always the line going parallel to the optical axis like this. Okay, so this light gonna bounce out like this, right? And it's gonna bounce such that the end gonna meet at this point. That's what we're trying to draw here. So I will try my best to draw that carefully. So that's gonna look something like this. Not good enough. Something like this. Try again. Try again. Okay, I'm gonna do it manually. So something like this. But sometimes this application is a little bit too smart in terms of how I draw the line. But in general, I'm just a really bad, artist in general. Okay, so it's like that. So that's the first thing. So what about the second light ray? There are many ways to do, but the one that I like is the light going into the center of the mirror, which is the same as for the lens. Remember, the light going through the center of the lens is not bended in any case, right? So it's just going through. But this is a mirror, it has to reflect, right? So it's gonna go in like this. And it's gonna reflect back like that. And the way it's gonna reflect is this angle is the same as that angle. Because it's similar to the case where you go through the center of the lens, right? So remember, if you go through the center of the lens, you will just get through the center like that, right? And then for the lens, you just flip everything here onto the other side. So that's how you can imagine it also. So that's gonna be the second light path that we use. It's gonna go like that and go like that. Okay, so you can see that the light coming out, which is this one, and this one, okay, they do not intersect. Again, similar to diverging lens that we talked about last time. They are not intersecting each other. But if you look at this light ray, your eyes will get fooled by the path of the light. So in order to find where the object is, right, so you have to extend the direction back and see where they intersect each other. So that's going to be here. So I forgot to write that this is an object. This is an image. Okay. So that's the ray tracing diagram for convex mirror. Now let's confirm everything using the lens and mirror equation. 1 over f equal to 1 over so plus 1 over si. And again, f is minus 20 centimeters. The object distance is 30 centimeters. So I can solve for si. So 1 over si is just minus 1 over 20 minus 1 over 30. Okay, so let me quickly calculate this. 1 over so you get si equal to 12. Minus 12, sorry. Okay, don't forget the minus sign. So you can see that the equation is exactly the same as the diverging lens. So we can kind of interpret this result in a very similar way. So first of all, it's a negative sign, right, for Si. So what can you say about this? It's negative sign. It means that the image is virtual. And that's what we have for the ray tracing diagram, right? The light ray does not really intersect at any point. You have to extend the light back and they meet at one point. So that's the image, which is virtual. The image is also upright instead of upside down, which is fine, right? Similar to the diverging lens. But now the image is behind the mirror. That's the only difference. And behind the mirror is kind of equivalent to having the image on the same side as the object, if you talk about the lens, right? So if you think about it, it actually makes a lot of sense that the image is behind the mirror, because everything is flipped, right, compared to the lens. Right? So that's the only thing you need to be careful about when you talk about the image for the mirror, right? If you have virtual image, the image is behind the mirror. If you have virtual image, the image is on the same side as the object for the lens. Okay, so lens or mirror, that's gonna make the location of the image differently. But in terms of the number that you got from solving the equation, it's gonna look exactly the same. Okay, so you need to kind of interpret this a little bit differently, but other than that, it's the same as the diverging lens. Okay, so nothing too new here. So everything should be really familiar to you. Okay, so this is for convex mirror, and I gotta go back to this image before I talk about concave mirror. So this is kind of like a more detailed ray tracing diagram compared to what we draw in the previous page. It's the same principle. The one that we drew is this one. And then you can see that the ray bouncing back so that at the end it goes to the focal point there. And then the other one that we drew is the one going through the center and then bounce out like this. Okay, and then extending back is gonna meet at that point, and that's where the image is. Okay, and you can repeat every other ray, and they're gonna do the same thing, right? So, but in our case, like 2 rays enough to pinpoint where the top of the image gonna be. So let's talk about concave mirror. Concave mirror is just the opposite of convex mirror. Again, you start from a spherical mirror, a spherical object, and then you just cut it. But now you coat the mirror on the other side. So the shiny part is here. Okay, so it's bounced a little bit differently. You can see that this kind of mirror, which is concave mirror, gonna converge the light ray instead of diverge it. So the behavior of this is gonna be similar to convex lens or converging lens. And you can probably guess already that everything is gonna be the same except the image is not behind the mirror but also in front of the mirror. Okay, so we're gonna draw the same ray tracing diagram for the example. So maybe I should go to the next page here. So example again. So I'm gonna use exactly the same value for here as here, but I'm gonna change this to concave mirror, but the radius of curvature is gonna be the same. Right? So we have concave mirror with r equal to 40 centimeters, and then the object is at 40 centimeters, so that's gonna be our SI, right? SO, sorry. So where is the image? So let's do this. R equal to 40 centimeters. So we can say right away that F is again R over 2. So that's going to be 20 centimeters. And because this is a concave mirror, the same behavior as converging lens, so the focal length is positive. Right? So you can explicitly write positive here, or not, it's fine. At least you know that it's not negative. Okay, so it's positive 20 centimeters. So let's draw the ray tracing. And as always, we start with an optical axis somewhere here, right? And now the mirror is going to be, let's say, here. And let's put some eyelash here. Okay. And then F is going to be 20 centimeters. Sorry, allow me to change one thing. I think back then I used 30 for the object distance. Okay, so let me change to 30. So the focal length is 20 because radius is 40. Focal length is half of that. And I'm going to use one grid. Again, equal to 5 centimeters. Okay, so because when light coming in, they're going to get reflected like that. So it's converging the light onto the left-hand side of the mirror. So it probably makes sense to dot the focal point on the left-hand side of the mirror, and it's probably here, right? So 1, 2, 3, 4 grids. Each grid is 5 centimeters, so 20 centimeters is there. That's our focal point. The object is 30, so the object is here, right? 1, 2, 3, 4, 5, 6 times 5, that's 30 centimeters. Okay, so that's the object, OBJ. Now, let's start with the first line again. The first line is always going to be the one going parallel to the optical axis like that. Okay, so the mirror will reflect such that the light ray gonna get converged at that point. So we know that our first light ray has to bounce from the mirror and then go through that focal point. It's gonna be like this. Okay, it's good enough, like this. That's the first ray. The second one we're gonna do is the one similar to what we drew here, the red one, which is the one going through the center, okay? And it's gonna bounce with the same angle. So it's gonna be going like this. And then it's gonna bounce out like this. Okay? Now, one thing that you might get confused is that the intersection happens where? Between the two lines. Is it here? No, that's not the case. Right? Because the light, even though the paths that we drew meet at this same point, but they don't meet at the same time, right? Because this thing has to go here and then here to get here, but this thing only traveled that much. Right? So that's not the real intersection point. The real intersection point actually happened here. Okay, that's where the two light ray intersect, which is back there. And that's where the image gonna be. So this is our image, which is far back here. All right, so that's the ray tracing diagram that we can draw. So you can see that the image is upside down and the light ray really intersect here. So you probably have some hunch that it's gonna be real image, which is upside down. So that means Si, when we solve the lens equations, should give positive number, right? So let's try that. So the lens mirror equation, one over F equal to 1 over SO plus 1 over Si. One over F is 1 over 20. The object is 30. So what is Si? Well, Si is 1 over 20 minus 1 over 30. And let me calculate this quickly. That's gonna be 60. Sorry, I shouldn't write it this way. This is wrong. So 1 over Si is that. So Si is equal to 60. Okay. So what I just did is a classic mistake that people do on the exam, that you forgot that it's 1 over and then you get confused. Okay, so try not to do this. Well, the thing is that if you get S and then you forgot to, like find the reciprocal, then it's gonna be way wrong. And if it does not agree with the ray tracing diagram, then you know something is wrong. So you double check that, okay? Anyway, this is what I got, Si equal to 60. So it's positive. That confirmed my suspicion before that it should be a real image. So Si should be positive. And it's upside down, right? But in this case, because it's a mirror, real image appear on the same side as the object, where for the converging lens, the image is on the other side, right? Which again, I think it makes a lot of sense this way. You cannot go into the back of the mirror, right? The light cannot enter to the back of the mirror. And let's see if it agrees with the ray tracing diagram. So our image is here. So how many grids away from the mirror? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, that's close enough. It should be 10. Well, no, it should be 12, but it's about 11. And again, it's because I didn't draw this super accurately, but it's good enough, right? It's good enough. It's not like, 0.1 or something like that. Okay, so for concave mirror, again, you're gonna get the same behavior as converging lens. So that means there's also possible that you're gonna get negative SI, right? So I'm not gonna do that. I'm gonna leave that to you because it's gonna be the same as the converging lens, right? So for concave mirror, you can have positive or negative SI, means that you can either have real or virtual image, depending on where you put the object. Okay, so you can try and then see how that gonna change things. But again, this is really nothing new. What you learned already from converging lens applies here. And the image, more accurate image is like this. Okay, what we drew in the previous page is this line, which bounds through the focal point of the lens, of the mirror, sorry, here. That's the first one. And the second one is going to the center and then bounce out with the same angle. And they meet at the same point here. Another one that I didn't mention that you can also do is for the light to go through the focal length first, the focal point first. And then the light coming out will be parallel. So this also works, but we didn't talk about that. But you don't need it, okay? You only need two lines. So just to eliminate any potential confusion, let's just stick with these two lines here. Okay, so this is concave mirror, and that's pretty much all the geometrical optics that we're gonna talk about here. So it's probably a good time to take a break, and then we're gonna come back and wrap up, material for the midterm, which is the last topic, which is interference of light through a double slit. All right, so let's take a 10 minutes break, and then we come back and conclude our midterm material. So see you in a few minutes.